Looks like we're live. Hello everyone and welcome to yet another recreational programming session with Mr. Zuzin. Hello everyone, welcome. Let's make a little bit of an announcement on our Discord server. Right, so I'm gonna do a red circle for better visual representation of what we're doing live on Twitch. And what are we doing today on Twitch at .television? Yes, the top level domain .tv means television. There's nothing you can say to convince me otherwise. It means .television. And today we're doing a web dev in assembly. Right, that's right. So I'm gonna give the link where we're doing all of that, https twitch.tv/sodding, and I'm gonna ping everyone who's interested in being pinged. And there we go, the stream has officially started. Hello everyone, welcome. Really glad to see you all today. So today I would like to explore a very interesting assembler, right, which is called flat assembler. So it's very interesting how much underrated it is. When people do assembly, they usually think about things like NASM, right? So I don't even know how it is translated. It's something like a it's not that NASM, goddammit. It's this one, net wide assembler, right? So I forgot what N stands for. And some people maybe think about things like GAS, which is a GNU assembler, and stuff like that. But flat assembler is actually, like, nobody really heard about it, but it's a very interesting assembler. It's a very interesting assembler. So let's actually try to explore that assembler a little bit. I'm going to do a probe, and so I'm going to do fasm. Yeah, I'm going to just put fasm. So essentially, we can take a look at the executable itself. I think the executable itself is rather interesting, right? So which fasm? It's located in user bin because it comes in the repos of the Debian, right? So I'm using Debian as a distro, and we can just like go ahead and simply copy paste that executable, literally copy pasting that executable to here, right? So it's a relatively small executable, but 142 kilobytes and stuff like that. But what's interesting is that it's it's actually not a statically linked executable, so it does in fact depend on libc. This is something unexpected, because if you, for example, write a hello world in fasm, right? If you write hello world in fasm, so let's actually Google that fasm flat assembler ELF64 example. There we go. Yeah, there we go. So if we just take this entire thing and just do something like hello ASM. So format ELF64. Do I even have a fasm mode? I don't even have a fasm mode. So let me maybe find a fasm mode for Emacs. I remember there was like some very simple fasm mode that we could probably steal from somewhere. I think I'm gonna do a very straightforward thing. I'm gonna just like do the chat move. I'm going to download this entire thing like so, and simply open this entire stuff and evaluate the buffer, and then essentially take my hello world ASM, and that should allow me to just enable fasm mode. And there we go, I have a fasm mode. No package manager involved, no anything. I just downloaded the file, I just executed it in my Emacs, and there we go, it just works, right? So no fuzz, no package managers or anything like that. It just works. So we need to produce ELF64 executable, right? And essentially, usually what you have in Linux applications, you usually have two segments. One segment is executable that holds the code, right? So this is where you're gonna have the code with instructions and stuff like that, and one segment that is readable, writable, which holds the data. Usually you want to use this segment for strings and stuff like that. So for instance, you want to have a message, you want to print hello world, so you basically allocate a bunch of bytes, and those bytes represent hello world, right? So, and essentially you probably want to put a new line at the end of the string, so you put 10. So and this is going to be stored in this readable, writable section, literally in the data section, right? So then you want to define your entry point, like where the program starts. We want to do something like entry main, and this is where the program is going to start. And essentially, to write a hello world in assembler, what you need to do, you need to perform two syscalls. two syscalls. Syscall is essentially user program asking an operating system, do something for me, do something that I personally, as a user program, as a pleb program, cannot do. For example, writing into standard output. User programs in Linux, they cannot write into the standard output. They can only ask operating system, okay, I have this string. Could you please write this thing into the standard output? Right, so, and the way you call a syscall, the way you ask operating system is by using the syscall instruction that comes with x86-64. So x86-64 has a specific instruction for asking operating system to do shit for the program, right? It was designed to have an operating system. At least this is how I personally understand it. Maybe it's completely wrong. I'm not a low-level person. I know it's hard to believe, but I'm not a low-level person, right? I'm not really that knowledgeable in these like low-level assemblies and stuff like that. So, but this is just my, you know, high-level Java developer understanding of how all of these things works, right? So this is a specific instruction, and essentially it will just jump to the kernel. But how do you say exactly what kind of syscall do you want to call? Right, so you have to put the number of the syscall into the rax register. You know, as we all know, the CPUs have a bunch of registers. x86-64 has, you know, a lot of different registers and stuff like that. Some of them overlap. Right, so for example, rax also overlap with EAX and also overlap with AX, which also overlaps with AL, and so on and so forth, right? So this is basically to preserve backward compatibility and stuff like that. So you need to put the number of the syscall that you want to, you know, call to rax. So on the internet, there is a pretty cool table of the system calls, right? So it's provided by Chromium OS, right? So if you do Chromium Linux syscalls, you will instantly find that, because Chromium OS is basically Linux. So all of the Linux syscalls, they actually work there. So this is the thing that usually floats on top, and it's very convenient, and it's like very like more or less up to date. Maybe I should not use it. Maybe I should use this one. Maybe there is a more fresh version. So yeah, maybe we should use the fresh version, but there we go. So it's x86-64. So I'm gonna actually copy paste this entire thing in here. Right, so I'm gonna copy paste this entire thing in here, and also in the description, this thing is going to be available. Right, so what do we want to do? We want to perform a write syscall. So here's the write syscall. The number of a write syscall is 1. It is 1. So let's go ahead and literally put 1 into rax. And it literally corresponds to a function write from POSIX. It literally corresponds to that. By doing a syscall write, you literally calling this function. So the next thing you have to do, you have to provide 3 arguments: the file descriptor, the pointer to the buffer, and the size of the buffer. How do you provide such arguments when you perform a syscall in assembly? You provide it also through a registers, and there is a call convention in Linux x86-64 that says that first argument of call is going into RDI, the second one is going to in RSI, and the third one into RDX, right? So you can actually provide more, up to, I suppose, 6 arguments, right? So, and you have to use this specific instruction then here. Since we have only 3 arguments, we only need RDI, RSI, and RDX. So let's go ahead and do that. So RDI. So what we need to move into RDI? We have to move the file descriptor. So the standard output is 1, if I'm not mistaken, right? So the standard, I think it is. I think it's just 1. Right. So the next thing we have to provide the buffer. So, and the pointer to the buffer is the message, and the size of the buffer goes into RDX. And the way you compute the size of the buffer, you can actually basically hard code it. It's not that big of a deal. Right, so 13 characters plus a new line, we can put 14 in here, and that will work, but there are better ways to do that, right? And that's it. So that is literally equivalent to doing write 1 hello world 14, and not even like that, so more like this, right? So that's what it's equivalent to. So, and yeah, so we just did a call right. And the next thing you have to do a syscall to exit, right? So what's the ID of the exit syscall? So we can also look it up in the table. So if you find exit, it's actually 60, right? So it's actually 60, so we have to put 60 in here. And in RDI goes the exit code, right? So you have to put 0 in here and call this syscall. And that is it. So that's basically hello world in assembly using x86-64 syscalls for Linux. You just perform 2 calls. This is literally how you would do on like in C as well. It's just like a single syscall requires these sort of preparations. But apart from that, everything is pretty straightforward. You have Elf file. Elf file consists of 2 sections. The one holds the data, another one holds the code. The one that holds the code is executable. The one that holds the data is writable. I'm not sure if it needs to be writable, but I guess it's fine. Right, I guess it's fine. So the next thing you do fasm hello.asm, and there you go. It wrote 236 bytes. So this is a file, 236 bytes, right? And it is hello. So, and interestingly enough, if you take a look at this file, it will say that it's an L file. It's an L file of 236 bytes. And it's not even executable. So one of the things you have to do, you have to mark it as an executable. So I just marked it as an executable. You can try to run this entire thing, and it says hello world. And executable is smaller than the source. Yeah, exactly. And it produces like actually small static executables, right? So we can take a look at inside of it, and there you go. It's an L file. It's a legit L file. There is some binary stuff, which is probably the code. And at the end, we have our hello world string. And that's a self-contained small Elf executable that only uses Linux syscalls, and it will probably work on your machine as well on any distro if you have a Linux kernel. So, because it doesn't depend on libc and stuff like that. And you know what's interesting about fasm? You know what's interesting about fasm is that we can Google it up, like fasm source code. So let's actually find, so what's the language it's written in? So what's the language it's written in? It's written in itself. This motherfucker is written in itself and it's self-hosted. I'm going to give you the source code of this entire stuff, right? So I'm going to put it in here. Right, so I already started because it's such an awesome project. And of course, I'm going to put that in the description as well. So it's a very small thing that produces other small executables that work, and it's self-hosted. And here's the thing. So the reason why I wanted to look into the executable is that I thought maybe it's basically linked and compiled the same way as it compiles other executables. So I thought that maybe the fasm itself is going to be, static, right? But specifically on my machine, it is not. It is actually dynamically linked with libc. I have no idea why. Does it really use libc? I don't remember it really using libc, because I remember a long time ago trying to compile fasm from scratch using this source code, and it produced like a static executable. Why this specific thing links with libc, I don't really know. Maybe it's something, it has something to do with the maintainers of this thing. Maybe the maintainers of Debian just compiled it this way. So yeah, but by itself, fasm just produces these static small executables, which I really like. It's kind of a cool idea to have some like small little thing with which you can experiment and stuff like that and explore the low-level world and everything. So, and what I want you to do today, right, so fasm, even though it's very simplistic, it's very small, it has a macro capabilities, right? So it has a macro capabilities. One of the macro capabilities it has, it can, for example, have a compile time constants like message length, right, equals where you can say, okay, so take me the address at the current line, like $, and do minus MSG, and essentially you have the length of the message, so you can just use like a message len, and if you modify this specific thing, you don't have a hard-coded value anymore. This is nothing special, like a lot of assemblies have stuff like that. Right, but furthermore, you can have a lot of other interesting things. For instance, you can create a macro substitution, very convenient ones, where you can essentially say, okay, like I don't want to call write syscall like that. I want to be able to just, you know, call it like I do in C. And in that case, you can do macro write, and let's say you accept the things that the write syscall actually accepts, right? So it accepts fd, buffer, and count. So we can say fd, buffer, and count. Right, so, and essentially you just take this entire thing and copy paste it in here, right? So syscall is hard-coded, is going to be 1, RDI, FD, buffer, and count, right? And in here, instead of doing like move syscall and stuff like that, you'll do write 1 message len. So maybe NASM also has something like that, but the selling point of fasm is that it's so simplistic, so small. Right, so I can do just fasm like this, and there we go, it still works. And if I call this entire thing, call this hello world, it's still full bar, right? So I changed hello world to full bar, so it got reflected in the output. So I can do that one more time, and this is hello. Right, and I can do the same thing with exit, right? So I can do macro exit, and here I supposed to accept the code, and essentially here, I can now move this entire thing to here. So this is going to be the code, and then I'm going to say exit 0, and this already looks like a freaking C. So when people say that C is very close to assembly, this is literally what they mean. This is literally what people mean when they say that C is very close to assembly, right? It's just like one step away from C. So yeah. It's like one step away from C, and yeah, now it's more readable, right? So I don't have to try to parse this kind of stuff. I can just tuck it away behind the macros, and it essentially works. Maybe I can do the following things. For instance, I can have a set of constants like syswrite, which is going to be 1, right? So, and I'm going to just do it like that, syswrite, and here we can have a sysexit, and it's going to be sysexit 16. There we go. So now I have all of the constants that I usually have, then the all of that stuff, and I can just like program like this, and it is very, very convenient. So you can go even further, as far as I know, right? So there is an article in here in flat assembly. So understanding the flat assembly. So they basically going into more like a philosophical part of fasm. This is fasm, by the way. This is fasm. Right, so they're going into more of a philosophical part of programming in fasm, and essentially what they say that fasm is not particularly an assembler. They say that fasm is an interpreter that outputs assembly code. Fasm is not a compiler. It's an interpreted language, the side effect of which is outputting the binary. That's how you're supposed to think about it, and they explain that from the philosophical ideological point of view, and this is actually super cool. I really like that. So they say that these assembly instructions are in fact just write to the standard output command that outputs that specific instruction. That's what they are. And because of that, one of the things you can do things like this. You can say repeat 5. So essentially what this thing does, it literally copy-pastes the code between these brackets 5 times. So essentially what we can do, we can say, okay, do write 5 times. So it's not going to be a runtime loop. It's a compile time loop. It's a compile time loop. Right, so when I can do something like this, and as you can see, it says hello world 5 times. How does it work? It literally copy-pasted this thing 5 times, and this thing 5 times got expanded into 5 write syscalls. So it's more like a preprocessor, right? It's more like a preprocessor. And you can actually have a lot of complicated things in here. So in fact, the thing I did in here, the thing I did in here, is actually a compile time variable. It is in reality a compile time variable. So you can do things like x equal 1. And then at some point here, you can say, okay, x now equal x plus 2. So at this point, x is going to be equal 3. So x is going to be equal 3. You can use x in here. And as you can see, there will be 3 hello worlds in here. So this is an interpreted language. It's an interpreted language, the side effect of which is outputting assembly instructions, not assembly instructions, but machine instructions. So, and it also has if conditions, it has loops. You can do a lot of interesting shit in it. I do not fully understand it. I do not fully understand it. And this is something that I would like to explore today, actually. And furthermore, I had literally the same idea a very long time ago when I was working on BM. Who remembers BM, by the way? Do you guys remember BM? Virtual machine? Virtual machine, I don't know. So essentially the idea of BM was to create like a virtual machine with its own bytecode, with its own assembly, but on top of assembly have sort of like a preprocessor that allows you to generate it more efficiently. And we can take a look at some of the things in here. So bottom, maybe there's some still examples. I don't, okay, so there's some examples in here. So yeah, there is a SDL maybe. Yeah, okay. So you could have constants like this, right? So the compile time directives that they are prefixed with %. You have you can have constants in here. You can have like scopes. You can have for loops in here, right? So you can have for loops in here and stuff like that. So it like I tried to explore this idea long time ago, but not with x86 assembly, but with my own made-up assembly, with my own made-up virtual machine. And apparently, I'm not the only one who got this idea. I'm not the only one who got this idea. But on top of that, fasm is a very old assembly, right? It's been around for ages. It's been around for ages. And the community, the fasm community is actually extremely active. They're not really that well known, right? So they're not being sort of like these glamorous swag developers that tweet memes on Twitter and stuff like that. They're just like really little known. They're just doing their own things. But over the years of existing, this community created, for example, their own operating system entirely in fasm. They made their own operating system entirely in fasm. So operating system in fasm. I think it's Minuet or something. I don't know how this is spelled, but maybe the Google will actually show me. So does anyone remember how it is called, right? I remember it starts with how do you spell it? Yeah, Minuet OS. Yeah. So they created this thing. So it's written entirely in fasm. And it makes you wonder, like, how did they manage to do that? How did they manage to create like an entire operating system that looks like this, by the way? It looks like this is the operating system that is written in fasm. How did they manage to do that in assembly? The scariest language on planet Earth. All of the memes on Reddit, on programming humor, saying that it's a very hard language and you should never program in it. How such language, how it is even possible to use this language to create an operating system? But they managed to do that. They managed to do that somehow. So maybe the Reddit propaganda was wrong. Maybe it was wrong. So I suppose the way they did that is because they had a very powerful preprocessor, I think. So which allows you to basically program in C. So yeah, that's probably how they do that. So maybe at some point I'm gonna go just to read the source code of this entire thing. That would be interesting, I think. That would be interesting. But anyway, so I'm going to give the link to this operating system, right, for anyone who's interested. And the latest release. Look at the date of the latest release. It was this month. I mean, come on. How active is it? Like, people still do that, right? So this community is very much active. This community is very much active. So they just don't bother with cloud or anything like that because they genuinely like programming for the sake of doing programming. So Right, so let me actually put this thing in here so we know what it has. All right, what I want you to do, I want you to explore fasm a little bit closer, a little bit more intimate, right? So, and one of the things I want you to do, I want you to write like a simple website in it, right? So essentially, I already did stuff like that before on a very low level languages. So essentially what you do, you create a socket using Linux syscalls, right? So by the way, all of these socket API of Linux maps one-to-one to their syscalls, right? Things like, for example, I think we can do socket, right? So things like socket that creates the socket, things like bind that binds the socket to a particular port and stuff like that. They have corresponding syscalls. And furthermore, on Linux, on the current versions of Linux, even the sizes of the structures actually match. These things are basically entirely implemented in the Linux kernel. So you don't even need standard libc to use this API because you can use it directly. Right. So it is very dangerous to use it directly. A lot of people will tell you, especially the people who like to masturbate to undefined behavior, they will tell you, you're not supposed to depend on this thing because they can change at any point. You're supposed to use libc. Ignoring the fact that libc breaks their own ABI all the time, right? So, but anyway, I usually tend to ignore such people. Right. So you can just use this thing directly. Yeah, this is what I want to do today. I just want to see how easy or difficult it is to do something like that specifically in fasm. Right, simple website, just like, you know, open a port, listen to that specific port. If you have a connection, just to respond with a hard-coded HTTP response, and close the connection and wait for the next one. It's a very simple algorithm, in fact. It's a very simple algorithm. So yeah, that's the topic of today's stream. Half of an hour intro. How about that? Dab, dab, dab. So let's go ahead and try to write a simple, you know, simple TCP server, right? A simple TCP server. I think I'm going to continue working in here. So I'm going to rename this entire thing into website, right? So this is going to be website. We're not going to have hello in here. And essentially, let me maybe remove all of that stuff in here. We're not going to have a repeat. And I'm going to do fasm mode. So message. So do we want to print actually any message? We can actually say that this is start. So this is a start message and this is a start message. We can say starting web site. Starting website, maybe web server. Starting web server. And I'm going to just compile website. Boom. And some, oh yeah, there we go. So I forgot to rename this thing. So permission denied, and this is because you have to make it executable. What's funny is that you have to make it executable only once. After that, you don't have to make it executable over and over again, right? So I suppose this is because when you regenerate the executable, it doesn't delete the file. It probably just truncates the file. So, and I suppose truncating the file doesn't mess the permissions of the file. It's kind of funny that they implemented a lot of cool, sophisticated shit, but they didn't bother to make the output executable, which maybe makes sense, right? If we look at it from the philosophical point of view, this is not really a compiler, this is not really an assembler, it's an interpreter. It's an interpreter that outputs binaries. So what it does, it just like redirects its output to a file. And it's up to you how you want to actually interpret it. You want to interpret it as an executable thing. Well, yeah, it's up to you to make it executable, right? So it's not the job of fasm to interpret it in a certain way. It's job to just output binaries, and you do whatever the fuck you want with it. Right, so you ask it to be elf64. There you go, here's elf64. Right. Oh, you want it executed? Well, I mean, just do whatever you want. Like, who am I to tell you what to do? Am I right? Anyways, so this is a start message, and after the start message, what we have to do, we have to create le socket. We must create le socket. So I'll go ahead and do that. Right, so where is the socket? Where is the socket syscall? Here it is. So let's go ahead and create a macro for this socket syscall. I think I'm gonna just put it as a comment, and we're gonna have a macro. So le socket, we're gonna accept the domain, we're gonna accept the type, we're gonna accept the protocol. And in here, right, so the usual thing is gonna be move rex. So we're supposed to have like a sys socket. But what's the ID of sys socket? That's a very interesting question. We can just look it up in the table. Luckily, with looking up in the table, we don't really have to do that all the time. We have to only do that once per syscall, right? And after that, we can just reuse the same things over and over again. So, am I looking at the right thing? I think I'm looking at the right thing. So, just a second. Yeah, 41. So this is going to be 41. And in here, we're going to have RDI. We're going to put a domain in here. Then RSI. We're going to have type in here. And RDX is going to be protocol. So after that, we're going to perform a syscall. Right, we're going to perform a syscall. And the question is, what we have to put in the domain, type, and protocol? I don't quite remember, to be fair. Can you make a macro for string creation? I believe I can. I think there was even an example in the article that I linked. There was an example that shows how to do this kind of stuff, I think. No, it's not actually there. I think it's somewhere in the manual. And by the way, I forgot to mention, all of that, everything I said about macros and stuff like that, all of that is applicable specifically to the fasm version 1. They developed a fasm version 2 where they introduced a thing called flat assembler G. So essentially, they took that idea of being like a very powerful preprocessor to the next level. So they basically said, we are now architecture agnostic. We do not target any specific, CPU, x86, ARM. We don't care. It is up to you. All of these architectures are now libraries that you plug in, and this is like a sort of assembly engine. And yeah, so they have even more powerful macro system in here that allows you to even specify encoding for, for instructions that this system never saw before. So you basically have architectures as libraries, right? So, and it's actually kind of interesting. It would be interesting to explore all of that, but I never looked into that. Right, so it's something very sophisticated and very powerful, but yeah. Calm instruction pointer, like holy shit. And to be fair, this thing is a little bit underdocumented. So there's a couple of like articles and stuff like that, but a lot of explanation of how this entire thing works is done through discussions on their forum. Right, so basically their forum is documentation to this thing. Right, the manuals kind of help, but not kind of fully. There's some also like YouTube channels and stuff like that, so I don't know. But we're using the first version of flat assembler. And okay, so what I was saying is that there's an interesting version of a macro called struct. Not really struct. I think it's not struct. Yeah, I think it was instruct. I kind of forgot how it does. So you do that through a struct. Yeah, there we go. So you can define a structure, right? And structure works kind of like a macro, except when you do dot name, it basically generates a name of the macro dot that thing, right? So essentially, let me show you what I mean. You can create a structure like this, right? And it's basically like a macro. It is basically like a macro, meaning that if you do point 69420, it will just get expanded, right? It will just get expanded to xwx and ywy, but 69 actually in 420, but it will also prefix dots with point. So that's basically what it does. So it like handles these dots in a special way. But apart from that, it's basically macro. And one of the things you can do in here, right? So you can do something like this. So essentially, if you have just dot and space, it will replace it with the name that you provided in here. So essentially you can just have special message macro that automatically also defines message size, right? It defines the message itself and also message size. But I don't really want to go into that right away because I'm not 100% sure how exactly it's going to work. And it feels like it redefines existing DB, so I'm also not sure how that will work. So yeah, I'm going to leave it as it is, but I'm going to keep that at the back of my head. Right, I'm going to keep that at the back of my head. So anyway, so we need to call to socket somehow. We need to call to socket. So let me see how exactly we're going to do that. So one of the things I probably want to do, I want to find like TCP server in C. Right, I want to see some examples that I can steal. Gigs for gigs, okay. Get them. Right, gigs for gigs. We can use that, I suppose. Let's use gigs for gigs. Okay, so we're supposed to put AFNet, which means that the protocol, the domain of the socket is the internet domain. This is because the sockets can have different domains. There is a Unix domain sockets, right? So they're like sort of local pipe, and there's internet domain sockets, which are sockets to external resources on the internet, right? So usually, like majority of the resources are internet resources, so people don't really know much about Unix sockets, but locally on Unix systems they are still used. I wonder if we can even find some interesting stuff in here. Yeah, there we go. So here are different things in here. So internet, specifically IPv4, so you can also have IPv6. So Unix or local sockets, doesn't matter. All of that stuff that nobody uses. Who uses IPX? I kind of vaguely remember IPX protocols like a long time ago, but even like 20 years ago, I think they were already kind of outdated. So yeah, nobody uses anything except like this thing. Like everyone just uses that thing, and maybe Unix sometimes, right, for local things. People in 95, okay, 1995. But yeah, POSIX API still supports all of that. POSIX API still supports all of that, so we'll need to have IFNet. So we don't have this constant yet, so we'll probably have to define it somehow. So then we say that it's a streaming socket, right? So a streaming socket within the internet domain means TCP, right? It means TCP. And then, yeah, protocol is 0. So the idea is, so this is sort of like a catalog, right? You specifying the type of the protocol top down, right? So first you specify the domain of the protocols, the huge domain of the protocols. So you have a lot of different domains like Unix sockets, internet sockets, and like IPX and stuff like that. You pick a domain. Okay, so internet domain. We're talking about internet domain. Within the internet domain, there are different classes of sockets, right? So there's a sock stream, and because there's only one streaming socket within the internet domain, you can just put 0 in here in the place of the protocol because it's going to be TCP. Yeah, there's only TCP in that specific sort of like type of the protocol. So that's why you just put 0. So that's how it works. This is how at least I understand it, right? So, but if we try to compile this entire thing, I don't think it's going to work. Yeah. So there we go. It says undefined simple AFNet. I was trying to use this symbol in here, so that makes a lot of sense. We need to somehow define AFINet. So the question is, what is it equal to? We can try to find it in in a standard C library, or we can create a C program, right? So if I take a look at the socket page in here and just like copy paste this stuff. So maybe I also want to include stdio super quick, so I can output Scheiße in here. There we go. And just do printf IFINet d IFINet. So then we can do cco main.c, and we're going to instantly run this entire thing, and it's equal to 2. Okay, it's as simple as that. As simple as that. So now we can also take a look at what is sockstream. Sockstream, right? So what is it equal to? So it is equal to 1. There we go. Just stealing code from C, just stealing code from C, and there we go, starting web server. Nothing really crashed, but we don't even handle the error. So how can we know if this entire thing even succeeded? How can we know that socket actually succeeded? We can take a look at its return value, right? If the return value is negative, that means it failed. But where is return value located? We can do strace. That's a good idea, actually. We can do strace. Why not? So let's give it a try. Strace. There we go. It actually succeeded. So it returned 3. It returned 3. IP proto IP. Huh. It recognized 0 as that specific thing. That's pretty cool. And you know what's funny is that the executable that fasm produces, they have like almost no runtime. Like, yeah, they have no runtime at all. So you, in strace, you're gonna literally see only the syscalls that you put in there. So you have 3 syscalls, write, socket, and exit. And this is literally what you did in here. Write, socket, and exit. So yeah, because there's no runtime, there's no libc or anything like that. Usually if you just make a hello world in C, it will call shit ton of different syscalls. Like, okay, we can take a look at this thing that just outputs 2 lines, right? We can take a look at what strace of this thing looks like. So that's its strace. So the runtime just, you know, links with like opens dynamic libraries, allocates some memory and stuff like that, probably for the malloc, and only then it performs 2 writes. That's how much additional runtime you have in here. But I mean, the computers, modern computers are pretty powerful, so they can handle that. This is not the worst thing that they can handle, right? But it's just like when you just call this thing, it's like literally all the syscalls. There's additional syscalls in here, exec.ve, but I suppose it is coming from the program that executed websites, right? Yeah, because essentially, how you start a child process, you fork your process, and within the child process you perform exec.ve. So it is the child who must perform exec. So that's why we can see like exec.ve in strace, because it was basically injected into our child process for us, and then exec.ve replaced the current image with the image of the website, and already the website performed these 3 syscalls. Right? That makes sense. I think that in fact makes sense. Pretty cool, isn't it? Pretty cool. We can try to debug this thing as well, like step debug, and see how it modifies the registers and stuff like that. So that will be interesting. So the problem here is that fasm does not create, you know, debug information. I think there is no way to ask fasm to create debug information. So we have to do a little bit of a hackish thing. So let me show. So I'm going to go in here. So if I just do gdb website, yeah, so no debugging symbols found in website. Furthermore, you can't even break on main. There is no main. Main doesn't exist. You can't break on start. Start doesn't exist. There is no thing like that. So this as main. You can't do that. You can't do that. There's literally 0 symbols in here. There's literally 0 symbols in here. So people say that it has G. Okay, let's actually see. So I can people in the chat probably confabulating shit. I don't really believe that it has G, but maybe it's true. So let's actually give them benefit of the doubt. And there's no G in here. So the reason why you thought it has -G is because you probably saw that in other compilers, right? You saw that in GCC, you saw that in NASM, you probably like saw that in some other place, and you sort of extrapolated. You sort of extrapolated and thought that maybe it also has this thing. And this is basically an example of how GPT confabulate things, right? So GPT literally mimics people. Oh, there is a dump symbolic information for debugging. That's actually pretty cool. So let's actually go ahead and do that. So do we have to do it like this? I think options have to go in here. I don't really know how it works though. So output optional settings. Okay, so web site txt. All right, source file not found, so maybe I have to put it as website txt. So it's awesome. Yeah. Finally, oh my god. Okay, so there is a txt, but it's probably not txt, right? So it's probably I don't know what the fuck is that, honestly. So I can try to take a look at web or file, and it's just data. So you're supposed to. It's like we don't really know what the fuck it is. So what if I do GDB? So file format not recognized. It just like uses some custom file format. I don't fucking know what it is. Right. So yeah, it's kind of difficult to debug this kind of stuff, right? And people keep in the chat confabulating different things. But there's one way you can debug that. The one way you can debug that. In ELF format, there's a very interesting thing. It is called entry point address. It is called entry point address. So what you can do, you can break on that specific address that you found in the ELF file, and then you can run this entire thing. But you're not going to see anything. You're not going to see anything. So you need to like to enable, and you need to set as layout to assembly. And there you go. So here are all of your syscalls. But you see the pure assembly, right? So you see the raw assembly. But you can see the syscalls in here. You can literally see the syscall in here. Yeah. So apparently fasm comes with its own kind of thing. But it's kind of difficult to figure out, like, right off the bat how to use that, so I'm probably not going to use that. So this is the trick that kind of works, so maybe I'm going to work with that trick. We can actually use a better, debugger, right? Why do we have to use GDB if we can use something like GF? Right, so I'm going to do GF, and I'm going to do website, so let me see, so maybe I'm going to do it like that. And we're going to break specifically on that thing. So can I find the entry point? So I probably can just, highlight. Can I put it in here? No, I can't put it in here because GF doesn't really support that. It doesn't support inserting it like that. There we go. So maybe this is something that I have to contribute in there, right? So I can run it now, and there we go. So, and the cool thing that you can have in here is that you can quite conveniently see the registers, especially if you step, right? So as you can see, I'm setting up different registers, right? And then I perform the syscalls. And as you can see, after performing the syscalls, I have a starting web server, right? And after that syscalls, we have a couple of things modified in here. So, and you can see that rags became 21, right? So essentially, write syscall returns the result in rags. It returns the result in rags, and it usually returns the amount of characters that were written into the standard output, into the file specifically. Standard output is just a file. So, and if we take a look at how many characters we have in here we have 20 characters specifically, right? 20 characters specifically plus the new line 10, right? And this is exactly what we see in rags, 21 characters. So the Linux kernel told us that I wrote 21 characters. So we can literally see all of that, which is pretty convenient. Right, so the next syscall is supposed to be what? I forgot. I think it's a socket. All right, so let's actually set up the socket. Boom, boom, boom. And we are about to perform. Is it really correct, actually? So I have a net 2. It doesn't really feel correct. Because there is 4 things in here. Oh, syssocket, yeah, so syssocket is 41, which is actually, yeah, so everything is correct. So what's going to happen after the socket? So the result located in regs is 3, which is a really plausible number for a socket, right? So because basically by creating a socket, we created a new file, we opened a new file. We already have 3 files opened with ID 0, standard output is standard input, with ID 1 standard output, and with ID 2 standard error. So if we open another file, so the ID is going to be the next one after that, which is 3, right? And that's what we get. So we have the ID of the socket, the file descriptor of the socket in regs. And essentially, like, we don't really do anything with that thing, right? So we just populate the arguments for the exit syscall, and we just exit. So I suppose what we have to do, we have to save that socket ID somewhere, right? We need to save that socket ID. So let me see. So let's create something like sockaddr. How much memory should we allocate for storing the socket ID? How much memory should we allocate? So I mean, maybe 4 bytes is going to be enough. So I know that the directive db is byte, right? So this is 1 byte. Word is 2 bytes, so it's W. DW is 2 bytes. So 4 bytes is double word. Because of that it's DD. So this is going to be 4 bytes. And 8 bytes it's quad word, right? So DQ. So this is sort of like a cheat sheet that I want to keep in here just to remember, because I can never remember that. So I can only remember that by sort of like doing this mnemonic, right? I know that byte is 1 and word is 2. So that means 4 bytes is double words and quad word is 8 bytes. So we can just do DD, right? And you're supposed to put the value of this thing in here. So I'm going to put 0 in here. There we go. So, and essentially what we can do, after we call the socket, we know that in rax we have the file descriptor. We can just move the file descriptor into here, right, from rax. But we have to be a little bit careful, right, because it's 32 bits. Rax is 64 bits. So maybe we want to do EAX, right? And as far as I know, fasm also supports the syntax where you can literally say dword, indicating that do the 32-bit right. So because if I accidentally do something like this, I think it's gonna go over this entire thing and it will try to override this message, right? So it's basically gonna be buffer overflow. Right, it's going to be buffer overflow. So we have to be careful with this kind of thing. So it has to be dword. And if I remember correctly, if you do it like that, fasm is not going to even warn you about that. Oh, it warns. Operate size does not. Okay, so it actually warns you if like some write sizes and read sizes do not match. It's actually pretty cool. So I have to do dword instead, and it works, right? It works, and it will save it there. We can now check if it actually worked out. So let me see how to do that. So yep, I'm gonna try to refresh this entire stuff, and unfortunately that kind of killed the breakpoint. Let me see if the breakpoint is still there. So I'm gonna do read elf e. Right, so entry point is this specific thing. So I'm gonna break on that specific point, and I'm gonna just run this entire thing, and there we go. We're there. So yes. So here is the move, by the way. I think no, it's somewhere down below. Did I do that correctly? I cannot find this instruction. I can't really find this instruction. So here is the write. Okay. Oh, I think it didn't update the executable. It uses the old executable because there is this socket syscall. And then instantly the exit syscall. I think I need to actually refresh everything. So I'm going to try to recompile, and I'm going to just do this thing one more time. So gf2 website like this. Do I have break? No. So I wonder if there is some sort of a way to save that specific entry point, but I feel like it may change if something changes within the executable, right? So maybe some things get offset or something, so I'm not really sure. There we go. So here is the write. You know what's cool in here, right? It uses a relative address, right? It's relative to the current instruction pointer, right? So basically here's the current instruction pointer, here's the current instruction, and it's plus this specific value. But JDB has a very cool feature. It gives you like the absolute address. It gives you the actual absolute address. Right, and we can use that as a pointer. So we can literally say 4102, and I can say, okay, let's cast that to the pointer integer. You can do that, right, in GDB. So this feature comes from GDB, and then we can dereference this thing, and it shows us the value of this thing. We initialize that variable with 0 in here, right? So it's with 0, and as you can see, it is 0 in here as well. So that's pretty cool. So let's actually do step debug. So here is the write. So we wrote starting web server, and then we are creating socket, right? So if we take a look at the registers, we'll see that in here, in the register, in the result, we have 3. So, and we are about to write that 3 into the memory, into that little section of memory that we allocated specifically for storing the socket. And there you go, it actually wrote it there. So if you know the specific address of your variable and you know the type of the variable, you can just use this kind of trick and you can literally see it in the debugger. So without any debug information, I can already explore different variables and stuff like that. So that's pretty cool. So I stored the ID in the memory. I stored the ID in the memory. So people asking what is the GDB frontend is actually called GF. So let me give you the link to this frontend. So you can find it in here, and for anyone on YouTube, I'm gonna actually put that in the description. There we go. So it's gonna be in the description. Okay, cool. The problem is that creating a socket may fail. Creating a socket may fail. We need to check that it is, it is correct. We can try to make it fail, right? We can try to make it fail by doing something like this, right? So I can provide 69 for 20, and I suppose that will basically crash, right? So Iraq's is going to be negative, right? Because this is probably not correct combination of the arguments. This is probably not correct combination of the arguments. So let's actually try to do fasm. So write fail, this is because this thing is currently executing. So let's actually kill it, right? So then I'm going to try to recompile one more time, and I'm going to refresh it, and I'm going to try to break on this thing one more time, and let's just run it. Yeah, there we go. So let's go ahead. Let's take a look at the registers. It's still using the old. Yeah, it doesn't refresh. I remember if I press, yeah, it restarts GDB, but it doesn't reload. Toggle disassembly. So you can only restart, but it restarts it with sort of like the same thing, unfortunately. And the problem is that I don't like that I have to provide this executable one more time. But let's try to do that. Maybe this time it's going to be a little bit easier. Right. And let's go. So here's the first syscall, and here comes the second syscall, right? So the socket syscall. And let's take a look at the rags in here. Rags should become like, yeah, there we go. So that's the negative rags. We just provided bullshit in there, and we got a negative value. Right. So we got a negative value. So I suppose what we have to do, we have to check for a negative value. So the way we can do that, we can do probably right after we did the socket, we can do CMP rags 0. All right. And for example, if it's less than 0, we have to jump somewhere, right? We have to jump somewhere. For instance, we can jump to error, and in error, we can have a separate thing in here. So error is sort of like a separate section. Right, and here we're gonna maybe print an error message. So maybe we're gonna do, error mcg, error mcg len, and then we can say, so let's rename start with error mcg, boom, error like this. There we go. So, and after that, we probably want to exit with non-zero exit code with 1. To be fair, maybe we want to even write it into the standard error, right? So, and to not actually work with magical numbers, one of the things we can do, we can just define things like standard output, which is 1, and standard error, which is 2. So we can define these kind of things. And every time we write something, right, so here I'm writing into the standard output, right, so this is a standard output. And here, this is the standard error. I'm programming in C. Like, I'm literally programming in C. So in case of an error, write error message and exit with 1. I don't freaking know. I don't freaking know. So, all right, so if I do something like, yeah, let's actually repeat that. But now, instead of just compiling it, let's also run it and see if it will say error. There we go. Starting web server, error. So that's pretty cool. If we get back to like the correct arguments, it actually started. It actually started. So that's pretty progress. So people also suggesting to do something like exit success and exit failure. We can do that. Why not? So just to make it even more POSIX compliant, exit success 0, exit failure 1. So as far as I know, using equals means that this is like a compile time variable. So that means at compile time it can change, but this is not particularly true for these kind of things. They are more constants. If I remember correctly, in fasm you use EQ instead of equals to indicate that this is a constant, and that way they cannot be changed. The same kind of goes in here as well. We just do EQ, and this is a compile time constant specifically. Compile time constant specifically, and I really like how like easy it is to check for an error, right? So it's just like 2 instructions, like compare to 0, and just like bail out to the error section, and there you go. And if everything is successful, you just save this socket file descriptor. You just save this socket file descriptor, and now you can work with this specific socket file descriptor. So that's pretty cool, I think. But the problem here is that it's not particularly clear what's the cause of an error. What's the cause of an error? One of the things we can do, we can basically, before performing any of the operations like socket, bind, listen, accept, we can just log what we're currently doing. We can just log what we're currently doing. We can do something like write std out socket trace message. That's pretty long, but maybe it's fine. Right, socket trace message, and essentially instead of start, socket trace message, creating a socket. Right, creating a socket. So socket trace message, socket trace message that, blah blah blah. There we go. And if I try to run this entire thing, start len. There is no start len. Ready? Undefined symbol. So it is in 45. It says there is no start len, but this is not true. Huh? Is that because I still have to use equals in here apparently? Specifically here. So, all right. Okay. So creating socket. But if I go back and fabricate an error, 69420, yeah. So we know at which point the error sort of occurred. So we kind of roughly know where it occurs. So starting web server, creating a socket, and then error. So maybe if there was no error, we want to say something like okay. So okay message. Okay, msglen. All right, so there is a start, and then we're gonna query replace start with okay. Boom. Okay, web server. Okay. Right. So that way. So okay, message I didn't see because I'm supposed to call it like this. There we go. So undefined symbol okay. So because it's an okay message. Boom. So yeah, error. But if we go back and get rid of an error, just create a socket, it says okay. So now we are able to trace each individual sort of action, and if an error happens on some sort of action, we know where roughly it happened. So it will help us a little bit. Hopefully it will help us a little bit. So we can even like maybe prefix all of these things within for. to make it look like a legit logging, right? Because all of the logging frameworks, they have this sort of like a levels of logging, like info, warning, and error, and you feel like very enterprise. You feel very legitimate, very serious. There we go. We have different diagnostics at different levels. We can actually tweak the level and only focus on very specific problems and not waste time on other problems. You feel really good about yourself when you're using logging system like that, don't you? I think you do. So that's literally the only reason why people have that. So, and there we go. Look how fucking cool it looks. You just put a simple prefix info and it already looks legitimate. It looks like a serious program. Can you believe this shit is written in assembly? It must have been written in some sort of like a latest trendy JavaScript framework. Like, holy fucking shit, look at this level of logging, like level of tracing. What the fuck? Is this written in assembly? That very scary, difficult language that I saw in the memes on Reddit? How is that even possible? The memes told me that it's impossible to program in this language. Holy fuck? What the fuck? You must be insane. Oh. Anyways, imagine learning about technology through memes and really believing everything they say. Holy shit. And there is a lot of people like that. Anyway. So we created the socket. The next step after creating a socket is to bind the socket. And that is a little bit scary, not gonna lie, that is a little bit scary. So, because if you wanna bind the socket, you have to fill up a structure. A flipping structure. So you need to know the size of the structure. You need to know the amount of fields of the structure. You need to know the size of the fields of the structure so you know their offsets. And then you have to allocate enough memory for the structure, and you need to actually apply the offsets precisely so you can write things correctly into it, and only then you will be able to pass a pointer to the function. And this is something that we'll have to do in assembly. No, that's the scary shit all of the Reddit memes were warning you about. Oh my god, let's go back to JavaScript. Anyway, so we're already streaming like for 1 hour, and I think I want to make a small break. I need to refill my tea. So, and after that, we're gonna go ahead and try to tackle that impossible computer science problem of allocating a structure in a memory and actually filling it up. It's fucking impossible with some sort of a programming language that a lot of smart computer scientists spend years on implementing. It is literally impossible, an impossible computer science problem. Only Microsoft can solve that with C#. You can only do that in C# and not in any other language. It is impossible. But we're gonna tackle that. That is not going to stop us. The only thing we need is a cup of tea. So yeah, let's make some break. All right, I'm back with my tea. Mighty tea. I mean, I was trying to say mighty tea. Not what you thought, okay? So, what we need to do, we need to allocate a little bit of a memory for the structure. So, first of all, we need to understand what kind of structure we have to allocate, right? So if we take a look at the definition of bind, so we have a structure sockaddr. We can try to find the definition of the structure. I don't really want to search for the definition of the structure in my local source code because it's kind of difficult to find anything in there because it's like a glibc. You know what we're gonna do? I have an idea. What if we just like download something like Musel, right? And we're gonna grab Musel for implementations and stuff like that, right? So some other people may say, but that's cheating. To that, I can only answer, I cheated with your mom. I can do whatever I want. It's still gonna be website written in assembly. Still gonna be website written in assembly. All right, so I'm gonna be using that as a reference. I'm an artist. I'm a performance artist, right? And this is my reference. You know how the artists like look up pictures on the internet for reference and stuff like that. That's the same thing. That's the same thing. It's a reference in a monology. So yeah, so let's try to find the definition of this specific structure, right? So if we take a look at the bind, it's probably defined with open curly brace, right? So we can do something like this. So it's going to be like that. Boom, here is the definition. This is the art of grepping. The art of grepping. So knowing what exactly to grep to find precise place where the shed is located without any, IntelliSense IDE or anything like that. You just like craft a specific combination of characters and boom, you found it. And it's language agnostic. It is language agnostic. If you know how your language works, you can do that with a simple grep, and there you go. You find the definition. It's that freaking simple. And it's going to work 5 years after today, 10 years after today. Will your favorite IDE survive after 10 years? Will you be able to still use Visual Studio Code in 10 years? Will it still be there? Or maybe Microsoft will go bankrupt and this entire thing is gonna die. We don't freaking know. But even grep does not survive in 10 years. There will be some other tool that accepts a string and just searches for the substring in the file system. And that approach is going to work in 10 years, in 20 years, in 50 years. That's it. Anyway, so that's basically the structure. And that's a very interesting structure, right? So that's a very interesting structure. It has subfamily and subdata. Subfamily and subdata. But if we take a look at the example from the very reputable website called Geeks for Geeks, right? Very reputable website. They actually have 3 fields in here, which is like, what the fuck is going on in here? So what's the definition of server ADDR? The definition is actually sockaddr underscore in. Wait a freaking second. If I take a look at the definition of the bind, it's ADDR without in. But here we do in. What the fuck is going on? What the fuck is going on? We can try to find the definition of such thing. Of course, we can just put in there. And it's completely different. So there you go. So it has scene family, scene port, scene address, and some scene 0 to, I suppose, pad that specific thing to the size of sockaddr without underscore. And they also, furthermore, when they pass in this pointer, they actually casting that to a very specific thing. So we are using a different structure than the one that bind expects. And this is because this is a form of polymorphism. So essentially, you can create sockets of different domains like internet domain, Unix domain, and stuff like that. And bind is supposed to work with all of the sockets regardless of domain, right? And different domains may have different sort of parameters. So underscore in indicates that we are operating within the internet domain, and these are the parameters of the internet domain. So as far as I know, there is also UN, I think the UN. So there is a similar sockaddr, but with UN, and this is for Unix domain. Maybe it's actually located somewhere here. Yeah, there we go. So, and to be fair, I think they have different sizes actually. They actually have different sizes. So I thought that maybe 0 was added to pad to a specific size, but it's not necessarily true because for Unix domain, it's actually huge. Look at the size of this specific socket. Look at the size of this specific socket. And I think this is intentional, right? If we take a look at what's going on here, bind also accepts the size of the structure that you're passing. It also accepts the size of the structure that you're passing. It distinguishes the kind of the structure by its size that you pass. But what's interesting is that Unix is not the only thing that does shit like that. WinAPI does stuff like that all the time. Do you guys remember like the usual sort of pattern in WinAPI where you create a structure, and within the structure there is a field into which you're supposed to write the size of the entire structure? And they actually use it not really for polymorphisms, but for preserving backward compatibility when they extend the structure. Right, because you can have a user code that expects a very specific size of the structure, so it limits how much they can change that structure. Right, and because of that, they force you provide the size of the structure so they know what version of the API you're using without modifying, recompiling your code and stuff like that. So it's kind of like all over the place in C world. Right, and it's nothing particularly new. Right, and it's like this kind of stuff is in the level of the kernel. It's in the level of kernel. Very interesting. So anyway, what we want to do, we probably want to take the definition of the structure, right? So let's actually take the definition of the structure and maybe copy paste it somewhere here. So I'm gonna, that was really strange. I thought I managed to copy paste it correctly, but I didn't because I'm a dummy dum-dum. Okay, so we need to know the sizes of these fields, right? So we have these kind of fields. So this is port, family, port, and address. So what is a scene family? So it's defined somewhere here. Subfamily. We don't really know the size of this entire thing. So maybe we can do something like this. Can I just do that in C? Or maybe I can just find the definition of this stuff. Maybe I can just find it. So let's actually go ahead and do that. I'm going to do grep rn, and it's probably something like a type def, right? Type def. Can I just put something like this in here? Will it find anything for me? I think it didn't find anything for me. What if I remove? I think it has to be also egrep. Nah, it didn't work. I forgot the art of grepping, unfortunately. Where's type def? The fuck is this? It's even not like a C. It's an input to some sort of a preprocessor. Freaking. So usually the files that end with .in, they're input files for some sort of a preprocessor. So that means it's not the final file. It's like generated. Maybe depending on the platform, it could be generated differently, but anyway. So short is unsigned short, so that means it's 16 bits, right? So this is what we know, for what we know. Right, so this is basically 16 bits. Cool. So the next thing is, so in.h, import, another 16 bits, right? So all of them are essentially 16 bits. 16 bits. And what about that one? In address. Okay, so this one is a structure. All right, so this one is a structure, but it's a structure of a single field, and that field is actually 32 bits. Okay, so we don't really need to create a separate structure. We can just say that this is a 32-bit integer, right? So that's the easiest thing to assume in here, like 32 bits. And in here we have 8 bytes, and 8 bytes is 64 bits, right? So essentially, if we allocate, you know, it's kind of funny that these 3 fields add up to 64 bits. Right, it's just basically 2 64-bit numbers, right? So it's pretty straightforward. Pretty straightforward. So let's take a look at this thing. So they allocated server ADDR, right? So they allocated server ADDR. So maybe I'm gonna keep like all of this string information like here, and all of the actual data is gonna be located in here, right? So the actual data. So serve. So how did they call that? They called it serve ADDR, serve ADDR, and we're gonna have scene family, right? So this is a scene family, and 16 bits is a word, right? So this is gonna be like this. So then we have a port, which is another 16 bits, and then we have ADDR, which is 32 bits, which is a double word, right? So DD. And then we have a little bit of a padding, and I think I'm going to respect that padding. So we're going to have sin 0. And I can just use DQ, which is basically 64 bits. And, you know, is it really true? 8. I'm pretty sure it is, right? So 8 multiplied by 8, 64. Okay, so I had a little bit of a brain fart. I do remember how the math works, okay? Just had a little bit of a brain fart. So, and the next thing we can also define is something like size of serve ADDR, which is equal to current address minus the beginning of this entire thing. Right, and this is basically how we can allocate this specific structure. I think it does make sense, right? I think it does make sense. That's basically what it is. Yes. So maybe I'm gonna even put this definition on top in here, so it is kind of relevant. Maybe we're gonna even use the fasm struct thingy. Maybe we should use a fasm struct thingy, but I'm not really sure how exactly we're gonna do that yet. Anyways. So let's start populating things. We need to do this kind of stuff, right? So that means we need to take this stuff, right, and dereference this specific pointer, because when you refer to the name, you're referring to the address where that specific field is located. You're referring to an address. So in fasm, in Intel assembly, by dereferencing, you just put it in brackets. You're effectively dereferencing this thing. Right, and what we want to save at that specific address, we want to save if inet. But you have to be very careful, right? So because you want to do 16-bit right, so we want to say it's a word, right? So you want to say it's a word. Okay, and this one is very interesting. Okay, so here you have to provide basically the address, right, in the network order. So as far as I know, the order in x86-64 is the least significant byte, right? So, and the network order is actually most significant byte. And because of that, we have these sort of functions that revert bytes when necessary. So I know for sure if you are on x86-64, you always need to revert the bytes, right? So it's a little big engine. Yeah. So chat says little big engine. So as far as I know, in case of in ADDR any, you don't really have to do anything much, right? So if we go here and I say in ADDR any, I think it is equal to 0. I think it's straight up equal to 0, so we don't even have to worry about that. So let me see. So in ADDR any, so maybe we need to include additional stuff. I don't really remember what kind of stuff we have to include. So let me see what we include in here up there. So we have socket. Maybe we need to also include additional these things, net db, net inet in.h and stuff like that. So there we go. We definitely need this kind of stuff. Oh, it's 0. There we go. So, and 0 is represented by you know, all bytes being 0. So it doesn't really matter if like what is LSB or, you know, MSB and stuff like that. It doesn't matter. So 0 is 0. 0 is 0. So because of that, and then I think we can just use it as it is. So this is going to be like that. Move. But in our case, the name of the field is just sin ADDR. Yeah, it is sin ADDR. So we need to do it like that. And ADDR any, there we go. So, but what's the size of this thing? It's 32 bits. It's 32 bits. Okay, it's kind of interesting. Why are they filling them up in kind of a weird order? Because after that you have a port, not the address. But anyway, so it's just geeks for geeks, am I right? Right, so geeks for geeks. After family you have port, and then you have address, but they actually filling it up. Okay, Jesus. All right, so this is going to be that, and the size of this thing is actually double word, so it's a D word, right? It's a D word. Right, and then we need to say the port. Okay, and the port is going to be interesting. So I want the port to be 6969. but I can't really do that because it has to be, the bytes have to be in a reversed order. So I either have to implement h-tones, which I don't really want, but I could, but I don't want to do that. What we can do, in fact, we can do an interesting trick. So let's actually take 6969. This is in a decimal representation. Let's actually turn it in hex. Hex has a very cool side effect. It's basically one of the reasons why people use hex. So the reason why people use hex is because the specific bytes of a number are visible. Each pair of byte in hexadecimal representation is a byte, right? So basically this number is represented by 2 bytes. The first one, 1b and 39. So if you want to invert the order of bytes, you can literally do the following thing. And there you go. So this is essentially in a network order. So you can just like manually swap them, and this is the value that you basically have to put in the port. And it's going to work, right? So that's why people use hexadecimal representation, because you can see individual bytes, individual nibbles, right? So some people say that 4 bits is a nibble. Yeah, so you can, like, each digit in hexadecimal representation is a single nibble, which is 4 bytes. So 2 of them is 4 bits, so 2 of them is 8 bytes, a single byte. I keep confusing the terminology, okay? So I'm a little bit tired, but you get what I mean, hopefully. You get what I mean, hopefully. Anyway, so let's actually save this value to that specific field. So this is going to be worked like so. There we go. And we just filled up the entire structure. So I actually want to preserve the order as it is in the memory, right? Because in the memory, first we have family, port, and address. A 0, we're not going to put anything in there. It's basically the padding to preserve very specific size of the structure, I suppose. Very specific size of the structure, so that's fine. And yeah, there we go. We filled up everything. So the next thing we need to do, we just need to call bind, right? So we need to call bind. So in bind, in our case, it's going to be sockaddr. We already have sockaddr located in here, so we're reading it and putting it in here. So now we have to provide the pointer to the serve address structure. So what we're going to provide, we're going to just provide the scene family, because this is the first field, so it points at the beginning of the structure. So by pointing at that specific field, we point at the entire structure, right? We just point at the entire structure. And then here we provide the size of this entire structure. So that's basically it. So, and after that, we may also like to check for errors, check for potential errors, right? So in case of an error, we're gonna go to the error handling code and just like do it like that. So that's pretty cool. It would be also nice to maybe write a message, right? Something like write std out, and here we're gonna have, maybe I'm gonna even copy paste that specific line, and I'm gonna replace socket with bind. So now we have a bind trace information, right? So first we're saying what's the action we're doing. We're filling up the structure that explains what kind of socket we want to have. It's an internet socket at the port 6969 that accepts connections from anywhere, right? So because it's all 0. Then we perform the byte and then check for the error and so on and so forth. So, but the thing we need to have the bind macro, right? So we didn't create the bind macro yet. So let's go ahead and do that. I think that would be very beneficial for us and potentially the humanity. Who the fucking knows? I don't fucking know. Probably not. Nothing I do is beneficial for humanity. So here are the parameters. So sockaddr, addr len. There we go. So let's do move rex seize bind. So we need to know this thing. Move rdi sockaddr. Then RSI addr rdx addr len. So we have a lot of repetitions in here in how we do the syscalls. Maybe in the future we're going to define a bunch of macros, things like macro syscall 3. Doesn't it remind you something? Doesn't it remind you something? Right, where we could maybe even like a number and essentially we can just do it like that. Number, and then A, B, C. Right, and when we do bind, we can essentially do syscall3, sysbind, sockAddr, addr len, and like that. So yeah, people say port exactly. So yeah, and you can predefine like different syscalls and stuff like that. I'm pretty sure maybe you can even make this number a parameter of the macro itself, and maybe you can sort of switch case based on that or something. I don't really know. We're also kind of nice to explore if macro system has variadics. So, and basically do not pass this thing at all. But I mean, syscall is already taken, so we'll have to call it somehow differently. But that's an interesting idea nonetheless. Yeah. It's an interesting idea nonetheless. So then we perform the bind, and so we have a bind trace. So we need to replace socket with bind, and here say binding the socket. There you go. Binding le socket. Okay, so can I just now compile this entire thing? So I'm going to do fasm, website asm, no, fasm. There we go. So let's go through the compilation errors. So operand size do not match. Okay, that's very interesting. So it's at the 38. It's at 38. Oh, that's very interesting. Is that because when we do sockaddr, we have to... Ooh, this one is interesting. Because it's a double word, and we're okay, I see. It's a double word, but we're saving it to 64-bit register. So what if we just do dq and make it 64? Right, and every time we sort of like, yeah, I think that would be better. That would actually solve the problem. So let me see. So we bind, this is 64, and here I'll have to use racks in that specific case. And this is a keyword. Yeah, that would be better. It's actually kind of cool that it checks the sizes. I thought it doesn't check them. Yeah, all right. So it kind of checks the sizes. So undefined simple in address any. Did I define it really? I didn't define it apparently. Okay, so that's fine. So let's say that it's going to be 0. It's supposed to be 0. Undefined symbol sysbind. So let's actually define it. Sysbind. So the error messages are reasonable enough so far. I'm really glad. So let's find the bind thingy. 49. Okay. There we go. So do we manage to compile this thing? And we successfully compile this. Isn't that a poggers, meine Freunde? We can try to run it and see if it's going to be successfully run. There we go. So it successfully bound the socket, right? So creating the socket, bound the socket, and so on and so forth. Right. So one of the things we probably want to do as well is maybe close the socket at the end. When we print OK message, we probably want to go ahead and just close the sockaddr. Right. So just in case. So we deallocate the resources and stuff like that. Maybe we want to even do that on error as well. So maybe we're going to do that on error as well. But this is a little bit, probably dangerous. Probably not. Because what if you errored at the phase of creating the socket? So you don't have a valid socket ID. How can you close an invalid socket ID? You can't. You can't really close the invalid socket ID. And because of that, close will return -1. But I mean, do you care? It's not going to crash your application. It's just going to tell you, oh, you provided an invalid ID. So what? Right. If I provide invalid ID, it will return -1. If I provide valid one, it will close it and return 0. In both of the cases, it will just do exactly what we want. So who cares? Right? We're not going to check that. I'm not even checking errors for these kind of things. Like, we already got an error. I don't care if this message will go through. I'll just throw it and just die. So I don't think there is any sense in checking whether sockaddr is valid or not. Right. So what's the point of checking whether it's valid? If it's invalid, it's not going to crash our application. We're going to continue. We want to forget about this socket ID after we close it. After close, we already assume that it's invalid. So it doesn't matter if it was invalid before that. It just doesn't matter. But it makes the code simpler. Just not caring whether it's valid or invalid makes everything simpler. You see what I'm talking about? Right. Because this is something that I used to fuzz about for a long time, and it would make my code more complicated because I would have to make like additional checks and stuff like that. But if you just say, I don't care if it's valid or not, I'm gonna assume that it's invalid after it's closed. So it doesn't matter, just close it. So yeah, I think it simplifies everything. And when you're programming in assembly, you really want to go for simpler solutions because they're gonna make your life simpler, right? You're already working with a very terse language, so why making it even more complicated than it's needed? So the question is, will this web server in assembly win in speed a Rust Tokyo web server? This specific implementation, no, probably not. Because to be fair, the performance of the web server has almost nothing to do with how optimal this sequence of instruction is. It's more of a how well you handle the I/O, right? Because it's not really like CPU bound, it's usually I/O bound. So it's kind of like a different kind of problem that you have to solve. So I didn't think so, unless I specifically like work on better I/O handling. So in the current implementation, I don't think it's going to be faster. All right. So what we're about to use, we're just about to use like a regular reads and writes, right? And it's just like, nah, we're not going to even use send file right now. And people mention IO uring and stuff like that. Yeah, there we go. Okay, go. So we bound everything successfully. After we bound the socket, le socket, we basically said what kind of port we expect from it. The next thing we have to do, we have to listen to that le socket. We have to listen to that le socket. So what does it mean? So it also accepts like a second argument. It accepts 5 for whatever freaking reason. So I don't remember what it is. So listen, backlog. What is the backlog? Defines a maximum length to which, basically the size of the queue. So the maximum connections that you may have. Okay. Okay, good. So listen, sockfd. Let's define a constant, maxcon, right? So this is how many of these things you can define. And after that, we can do simprex0. If it failed, we just do gl error. So we can also probably want to have some sort of a tracing. So listen trace. Listen trace. Bind listen. Listening to the socket. No. Listening to le socket. Listening to le socket. So, and in our case, this is actually syscall2. Listening accepts 2 parameters. So let's actually just do something like this. And yeah, I want to use the exact naming in here. Then macro listen sockfd backlog syscall2 sockfd backlog. There we go, and that should be, well, I mean, sock2 probably has to accept the ID of the syslisten, right? So we have to define this thing somewhere here, and we're gonna put this thing here, equal. And what is it equal, meine Freunde? 50, okay. So this is 50, goes right after the byte. Okay, so let's try to build this entire thing. And a legal instruction. So we don't have close. Oh, okay, so if I go to actually define close, let's go ahead and define. So maybe I'm going to actually collect all of these syscall macros. Right, I'm going to be collecting these syscall macros and I'm going to put them in here. And for the macro close, which accepts just fd, we're going to have syscall1 sys close fd, right, and 1 is essentially I don't know if there is a better way of defining such syscall macros without repetition. So, but since I don't know that way, I'm just repeating it. As soon as I discover that way, I probably will get rid of the repetition. Right? I'll probably get rid of that. So max connections is not defined, so let's define them somehow. We're gonna have max connections. So how many connections we want to have? Let's say we're gonna have 5 connections. So queue of 5 connections. So sysclose is not defined. So as you can see, I can even use a compiler assisted refactoring here, right? So I can just use a bunch of things and right, just go to the compilation errors. Close, and the close is actually 3. People are having porth flashbacks. Yeah, because that's what porth is. It's just a preprocessor for assembly. That's what it was. And yeah. All right. And compiles. And the whole thing is 716 bytes. 716 bytes. So let's just try to run this entire thing and see what it says. Okay, so we successfully listened to the socket. We successfully listened to the socket. And the last operation that we have to perform, we have to accept the socket. We have to accept the socket. But interesting thing is that accepting will block. Right, accepting will block and will wait until we get a connection, and we'll have to react to that connection by writing into the file descriptor that we got. So let's try to see that. So let's take a look at the definition of accept. So what is accept? Accept accepts socket fd of the server, and it also accepts the pointer of socket address, the one socket address that we already worked before. But this time it's a separate socket address structure that is going to be filled up with information about the client that just connected, right? So we filled up this socket address specifically for the server. This is the server information, and we need to allocate the second structure, socket address structure, that is going to be filled up about the client information. So we need 2 of these structures. And this is probably where the struct macro is going to be useful. So probably I'm going to try to use it right now. I have a feeling that I want to use it right now. So let me try to see. So if I remember correctly, so I need to find where we talked about it. Yeah, here it is. So you define a structure. Then you can define my point and stuff like that. So let's go ahead and do that. So this is this. It did a really weird thing. I don't know what it did, but yeah. So we need to have these 4 fields in here. To be fair, I can just grab these fields, and that's what it's going to be. So we're not going to accept any parameters. So structures in here can accept compile time parameters, making them generics actually. Right, so it makes them generics. And in here, what we have to do is just something like this, right? So, and this is more of a server ADDR in. So this is the name of the structure. Yep. So the name of the structure, and how we use that like so. We just do server ADDR. So this is the name of the structure, and then the definition of this thing, like so. And that single definition is supposed to replace these 4 things, right? It's supposed to replace these 4 things. I wonder if there's a way to just take the size of this entire structure, but I don't really know how easy it is to find it. So there's also another restruct thingy. So defining data structure addresses by register or absolute value, blah blah blah. So micro instructions, see that. Yeah. So there's a lot of ways to define structure. So I don't know all of them. It would be really kind of cool if there was a way to just take the size of this entire thing, but we can compute it. We can just easily compute it. So this thing should automatically create this symbol anyway, so we will always know the size of this entire thing. So maybe I'm gonna even call it like that. And to create a structure for the server, for the client, I think we want to do something like CLI ADDR of the type serve ADDR in. So that way we have two structures of the same layout, right? So that's pretty cool. Size is mentioned in that paragraph. So size, yeah, okay, I can see. So you can automatically sort of, yeah, I don't like that you have to, I'm going to define two structures. I can do something like this, right? So I can say size is equal to maybe scene family, right? The beginning minus that. I can try to do something like this, but that means I'm going to have an instance of the size for each individual same structure, but maybe that's fine. Maybe that's fine. So it's a little bit annoying. I don't know why, but I guess that's fine. So that means serve ADDR, there will be size. Yeah. Okay. So let me try to recompile this entire thing. So we'll have to go through the compilation errors and see how it's gonna go. So undefined, okay, it's 4. So this means that this thing has to be just size, and it worked. Okay, so it worked actually exactly as I expected it. Huh. That's funny, actually. That is funny. Okay, that's actually super cool. All right. So size, would.size not be compile time only? It would, but I mean, that's not the problem that I have. All right, so let's try to run it, and it errored. So it literally errored. And I wonder what caused that. So what if I go back in what I've just created? So I really need to go back and get rid of this entire thing. Yeah, I'm getting rid of this entire thing, and I'm going to try to recompile this entire stuff, and it doesn't error. So it doesn't work exactly as I expected to work, unfortunately. So, so we're not going to go that route then. We're not going to go that route. So what I want to do probably is just to try to do it like that. Serve ADDR in. Let's try to recompile this entire thing and run it, and it works okay. So there is something wrong with that specific size thingy. So yeah, it didn't work the way I expected it. So, but that's fine. That's actually fine. We can just do serve ADDR, CLI ADDR. So let's run and compile it simultaneously, compile and run it simultaneously. So, and that seems to be working. Okay, so now what I need to do, I need to do accept. I need to do accept. So let me take a look at the accept. Ooh, it's accept 4. Right, so we need this specific accept. So it accepts sockaddr. All right, so we can provide sockaddr. So the next thing we have to provide the pointer to the address. So this is going to be CLI address. And it's suppose we're going to just give the pointer to scene family, right? So because this is where the structure starts. And here's the interesting thing. We have to provide the length as a pointer. We have to provide the length as a pointer. And furthermore, if we take a look at the example in a reputable website called Geeks for Geeks, so we also set the size of the structure to this specific variable that we provide as a pointer. So that means we need to allocate that variable somewhere. Right, so we can just do something like CLI ADDR len. The type of this thing is an integer, right? So the type, I think it is an integer. So what is a socklen? Fuck, what is a socklen? So I'm gonna, all right, so let's go to musil. This is actually very important. This is actually very important because if it's like not the size I think it is, we may have some sort of a buffer overflow. Type def, so here it is, it's unsigned. It's just unsigned, which means probably unsigned int, which probably means 4 bytes. Right, so which probably means 4 bytes. Okay. So that means we're gonna say dd and it's gonna be 0. right, dd0. But maybe we can go even further and just put this thing, because I suppose this is a compile time thing, right? This is a compile time thing, and it's gonna like literally put it as data in there. That's actually a 5-head move in my opinion. This is a huge 5-head move, right? So because we know the size of this thing at compile time, so we can just initialize it in memory like that. Okay. So let's put this thing in here like that, and that's the pointer basically. And of course it can fail, so we need to double check. And also we wanna, you know, accept message, accept. So in case of accept message, what we're gonna say? Query listen accept. There we go. So waiting for client connections. Yeah, waiting for client connections. Okay, so I outlined a thing that I wanted to do. I just outlined the thing. So let's go ahead and go through the compilation errors. So illegal instruction accept, right? So we do not have accept, which is fine, which is a rather expected thing. Right, so we want to have accept to. All right, so we have in here. So we have sockaddr, then we have address and address length. Then we're gonna have that accept address len. There we go. So that should be fine. So we also need to find the ID of accept. I don't know why I did it like that. What is the ID of accept? It is 43. Understandable. So it's closer to here. So it's even something like that. So they go in order. All of the sort of like a network API, as you can see, they're very close to each other. So which makes it kind of funny, right? Because exit is like 60. I don't know why it is like that. But yeah. So listen is 50. Okay, so. So let's go through the compilation errors one more time. So this is going to be fasm, website asm. There we go, and it compiles. So I'm really happy to see that. I'm super happy to see that. Okay, so one of the things we probably have to do, right? So accept returns the what is it called? The file descriptor, right? It returns file descriptor. So that means we need to allocate some memory to store that specific file descriptor. So we're going to have something like connection of D, and it's also going to be 64-bit integer, right? So 64-bit integer. After accepting, we just move keyword confd from racks. So we're just saving this specific thing, so then we can use it later. And one of the things we probably want to do, maybe we'll want to just close it when we finalize everything, right? So we write OK, then we close both of these things. And in case of an error, we're going to also close both of these things. Confd for a long time is going to be invalid thing. But again, we don't really care. We really don't. One of the things we can do, by the way, we can make them -1 or something. You know why? Because 0 is a valid ID. So that means if it will try to close 0, it will close the standard output, which is not particularly great idea, I think, right? So let's not close it. Let's try to close something completely fucking invalid so it doesn't screw everything up. You know what I mean? Right, so both of them initially can be, you know, something completely invalid. Right. So, and that seems to be working, All right. So now, if I try to compile, it seems to be compiling. So let's go ahead and try to, okay, it blocked. It didn't print okay. That means the entire call blocked. It is waiting for incoming connections. Right. So, and let's just go ahead and try to do that. Can I do that a little bit better so we can see what is going on? So we can try to do telnets 27.0.0.1 69.69. So yeah. We successfully accept the connection and the server actually closed that specific connection. All of that entirely in fasm using Linux syscalls. x86 69 syscalls. All right, so yesu, but here's the cool thing. So we have a conf-d, right? And this is a file descriptor. So that means we can write some shit into that file descriptor. For example, we can write a hello message, and we already have a write syscall. So we can do write, not std out, but conf-d, and we can have hello len. So who said we can't do shit like that? We can do shit like that. So let's go ahead and do that. So maybe we're gonna have something like hello from fasm, maybe flat assembler. So maybe we're gonna provide a new line. Let's provide a new line. Hello len equal minus hello. There we go. So let's try to compile this entire thing. A legal instruction hello, yeah, because this has to be db. There we go. So that seems to be working. That seems to be working. Okay, so we're waiting for incoming connections. Yeah, so I'm going to close a bunch of terminals in here. So let me readjust everything. And I'm going to do telnet 001 6969. So yeah. This is what we received from that socket. We connected to that thing, and this is what we received from the server. So we can already respond with some text. And since we can respond with some text, we can hard code HTTP response, because HTTP response is just a text. It is just a text. Let's go ahead and do that. So here we have hello, and let's just do something like response. So what we can do, we can just use it like that. And so what's the HTTP header? HTTP 1.1 header example. So list of HTTP header fields. List of HTTP header fields. Maybe I should have used Google, because this is kind of sadgy. This is kind of header field definition. Okay. So maybe we're gonna do status line. What about status line? HTTP1 response. Status line, general header. Okay, so HTTP version, right, and HTTP version by itself. I don't freaking remember, dude. Like, it would be nice if you just show me examples, status code definitions, HTTP responses. What is this gatekeep? Oh, okay, finally, somebody actually gave me working example. I swear to God, the gatekeeping is insane, dude. It's fucking insane. All right, so in HTTP, you're supposed to use /r/n, right? So it's going to be 1310, if I remember correctly, right? So this is going to be that. So, and then what we want to have, I suppose we want to provide like a content type, right? Text HTML. Is that how we do that, right? So something like this. I think that's how we do that. So content type header. Content type header. So yeah, it's content type, and what kind of things we can have. Okay, so do we want to say that it's UTF-8? I think it would make sense to say that it's UTF-8. Yeah, that makes sense. All right. So, and I remember a long time ago, because this is not the first time I do that, one of the things you want to say is the type of connection that you want to have, right? Because the modern HTTP is kind of crazy. The modern HTTP is kind of crazy, so it has like a keep alive stuff and everything. So you probably want to say that you're going to close the connection after you served the response, right? So HTTP header connection, right? So you want to have something like that. Connection close, yeah. So close indicates that either the client or the server would like to close the connection. This is default in 1.0, but we're using 1.1. So I think we want to actually say that explicitly, just in case, right? So just in case. So content length, I think it's not particularly necessary if you just close the connection, right? So if you just close the connection, I don't think it's particularly necessary, so whatever. So then we're going to have an extra new line. And after that, we can put whatever we want in here, right? So we can say something like h1 and just say hello from flat assembler. Hello from flat assembler. And since we're done with HTTP bullshit, we can just use the Unix new lines in here. At least that's how I justify all of that. So let's do response len, and it's going to be equal minus response. There we go. It's going to be equal to minus response. So, and you can just directly modify this thing in here, hopefully. So what that means now we can just replace hello with response, right? And try to recompile this entire thing. And let's not use telnet this time. Let's try to use the real web browser. Okay, something went wrong. That's very interesting. Maybe we have to provide the size of this thing. Oh, it worked. But it works only once. It works only once. Right, because then it basically exits. Right, then it basically exits. But it's not that big of a deal. What we can do here, we can just put that in a loop, right? So essentially, after you served the thing, you can just repeat it, right? So we can do something like a GMP next request, right? So this is unconditional jump. You always jump there. You always jump there. So, and I suppose you want to do next request somewhere here. Right, so you accept, which means you block, then we save that specific thing to a variable, then we serve the response, and then we do that again until we encounter an error, right, until we encounter an error. So if we try to do that, I'm going to refresh, and yeah, so that's pretty cool. Let me see, can I just see the network? There we go. So I keep refreshing. That's actually pretty slow for assembly. So speaking of weather, it's going to be faster than Rust, right? So it's pretty slow, I'm not going to lie. So let me put it like this. Yep. So we can serve shit from assembly. And what's interesting is that it's like 1 kilobyte, 1.1 kilobyte. And the only thing it does, it just calls to Linux syscalls. Just with Linux syscalls and a few assembly, not even assembly instructions, few machine instructions, we already can serve static context. Set TCP no delay to the socket. Yeah, this is probably something that I'll have to do, but I just don't want to spend time on that. But yeah, thank you for reminding me. Right, just think about that. Like, how much bloat do you have on software if this is the only thing you need to serve the static content? And I'm not saying that that we have to always do shit like that. What I'm saying is that just comprehend the level of bloat that people put on top of things that are needed. Right, so it's just like, yeah. So this thing is completely static. Even if, what's funny is that if I give you this executable and you have 64-bit Linux, it will just work on your machine. Without any fuss, you will just execute it and it will do the same on your machine. Because it doesn't depend on libc, on anything like that. It's just uses the syscalls of Linux that were that existed for ages, right? They didn't change much, I think. I think they didn't change much, right? So it will just work. No package managers, nor anything, no dependencies, or just single executable, 1 kilobyte of machine instructions, and it will serve like simple page. I think that's pretty cool. So that's very interesting. It would be also kind of cool to introduce some sort of a logic in here, right? Being able to route between different routes, right? So like handle the paths in here and URLs and stuff like that. That will require parsing the HTTP headers and whatnot. Right, so that will be cool. But we're already streaming for 2.5 hours, so yeah, I think the time for me has come to go. Thanks everyone who's watching me right now. I really appreciate that. Have a good one, and I see you all on the next recreation programming session with Azuzin. Bye bye. Love you all. Mwah.